Okay, so the idea that we are looking in right now is naming alcohols, and we have done this for alkenes as well. So it's pretty simple. The idea remains the same, which is that you're going to have a prefix part which tells you the number of carbon atoms, and then you're going to have a suffix part which in this case is going to be NOL. Okay, because for alcohols we write OL, right? And if I look at this molecule here, this has one carbon atom, which makes it meths, and because it has an OH, we're going to call this methanol. Okay, why? Because it has only one carbon. If you look at this one, this here is a two carbon molecule, so this is going to be called, two carbon is basically eth, so this is going to be called ethanol, right? And if you look at this one, now this is a three carbon molecule, three carbon is prop, and you know that again this part, which is basically just this part is going to be called propanol. Okay, now if you look at this one, this is a bute, a four carbon molecule is a bute, and you're going to have NOL, so this is butanol, right? So this is how we name the alcohol molecules. And if you had five carbons, you're going to call it pent for the prefix part, and the suffix then remains the same, which is OL, and there is going to be pentanol. Okay, so this is how the naming works for alcohols. And of course, the difference in naming, which was if you call it the bute 1 ol and the bute 2 ol like that, we're going to do that in isomers once we reach that part. Okay, so yeah, this is one thing. And now let's look at the other thing here, which is formulas, right? Very important, because I'm also going to tell you one important difference between the molecular formula and the structural formula. So I think we can just make the same table again. So we've got the name, we have got, let's say, we used to have the molecular formula. I'm writing this MF. Then we had the structural formula, and then we had the full structural formula, right? And what was the pattern that we were following? So we were using the full structural formula to figure out the structural formula, right? This is what we did for alkenes and alkenes. So let's now look at how we're going to figure this out in this stage, right? So let's say I have the molecule which we just studied, methanol. And if I were to draw the structure for this, so it's going to look something like this, right? Methanol, methanol, you're going to have an OH molecule, and you're going to have something like this, right? So this is the full structural formula for a methanol molecule. And by this formula, you can just see the molecular formula. You can also figure out the structural formula. How? So if you were to talk about the molecular formula, you need to remember for the molecular formula, what that basically tells you, let's say I have a carbon and I have CH. I have a carbon and I have a hydrogen. So the molecular formula is going to tell me that in a molecule, how many carbon molecules are there and how many hydrogen molecules are there. So let's say if I have a CH4, right? Now this CH4, if I were to break this in terms of a molecular formula, what that means is that you have one carbon atom and you have four hydrogen atoms. So at this stage, at the molecular formula, we don't really care about the structure. I'll tell you what the main difference is, but let's just try to figure that out. Okay, so you have what? If we were trying to figure out the molecular formula, so you have one carbon, you have 1, 2, 3, 4 hydrogens. That's 4 hydrogens and an oxygen molecule. Okay, so this becomes the molecular formula, which is CH4NO. Right, this is the molecular formula. And if I were to write the structural formula, now the structural formula will look something like this. So you've got a CH3. If you notice here, you've got a CH3. Right, you've got a CH3 and you've got an OH. So this is your structural formula. Did you notice the difference? The difference is that at this part we were just counting the molecules, right? We were counting different atoms in the molecule. So we are counting how many carbons do we have, how many hydrogens do we have, how many oxygens do we have. But at the structural formula, at this level, we're basically talking about the structure, how the structure looks, right? How the structure looks, you have got a CH3 first, so that's the CH3, and you've got the OH molecule at the second place. So you place the OH molecule like this, right? This is the difference between the structural formula and the molecular formula. At the molecular formula, you don't really care about the structure. You can write it either way. But at the structural formula, you have to write it in the proper format. Okay, so this is the one main differentiation that you need to take care in the CI paper as well. Right. So this was the first molecule. Let's take ethanol. Okay, let's take ethanol and let's draw ethanol first. So we've got two carbons because ethanol is 2. You've got a CH here, we've got a CH3 here, and an H here, an H here, and an OH molecule here. Now, how do we write this? Now, if we were to write the molecular formula, again, at the molecular formula level, we don't care about the structure. So we're just going to count the atoms. We're just going to count the different atoms. Okay. So we have 2 carbons. So we're going to write C2. Now we have 1, 2, 3, 4, 5, 6 hydrogens. So we're going to write like 6. And we have an oxygen molecule. So this becomes C2, H6. So this is your molecular form. We don't care about the structure. But if I were to now write the structural formula, then what? Now you have 2 carbon molecules. Structural formula, we care about the structure. Okay. So if I break it from the middle, you have got a CH3 here. Okay. And then you have a CH2 like this, because you can break it from here as well. You got a CH2. You got an OH molecule. So this is CH3, CH2, and an OH. So the structural formula is CH3, CH2, and an OH. Okay, basically what we are doing, we are basically just writing this in a structural format, right? The way just like the same way we did in alkenes as well. Remember, we were drawing the double bonds as well in the structural formula. So that's why it matters. Right. So let's take the third molecule, which was propanol. Okay, and if I draw the propanol structure, so I'll have to scroll down a bit. Yeah. So got the propanol. So that's how the structure looks like. Now for propanol, again, if I were to write the molecular formula, you can just count the number of different atoms. So you've got 3 carbons, so that makes it C3. You've got 1, 2, 3, 4, 5, 6, 7 in each. You've got 8 hydrogens and an oxygen molecule. So that makes it C3H8O. And that's your molecular form. If you were to talk about the structural formula, again, you're going to do the simple thing of breaking it down from the middle. So this is a CH3. Okay. Again, breaking it from the middle, so the CH2, and again a CH2, and an OH molecule. Right? It's very easy. So you've got a CH3, CH2, and a CH2, and an OH. Okay. Simple? Yeah? Right. Again, now we can just take one more molecule, and that's butanol. And if you were to draw the structure again, so this is 4 carbon. You've got hydrogens all the way. Just so many hydrogens, and that makes my handwriting very dirty because I'm tired of drawing out these hydrogens. Right. So you've got this butanol molecule, and now I need to figure out the molecular formula. So I know that I have 4 carbon. So this is C4, and I've got 1, 2, 3, 4, 1, 2, 3, 4. This is 9. 4 and 4 makes it 8. This is 9 and this is 10. So this is C4H10 and an oxygen molecule. So that makes it C4 CH10O. Right? This is the molecular formula. If I were to write the structural formula, I'll break it from the middle. So this is a CH3 here. Okay. Then you've got a CH2. Then again you've got a CH2. And you've got another CH2 and an OH molecule. So this is your structural formula. CH3, CH2, CH2 and an OH. So this is how it works. Now one more thing to notice here is that if you just look at all of these molecules, let's say now here I'll take the cleaner ones. Yeah. Now notice in all of these molecules, I have taken the OH part at the terminal carbon. Now here, because you only have one carbon, so that is the only place you could attach. But if you look at these places, even at this one, both of these carbons are in a way terminal carbons, because this is also one if I count from this side, and this is also one if I count from this side. So let's just leave those as well. But if you talk about now these ones, now here you have three carbons, right? And the terminal one is this one and this one. And if you see, I have attached the carbon at the terminal carbon, and I've attached the OH molecule at the terminal carbon. And even in this one, I've attached the OH molecule at the terminal carbon, right? Now this is not a way, you can say something and hard and fast rule that you only need to attach the OH molecule at the terminal carbon. You can attach it anywhere. Like for example, if I take this OH molecule and I attach it at this place, I can do that. What it becomes is that now this becomes an isomer. Why? Because for this, if I were to write the structural formula, this would be CH3, CH2. I'm writing for this one, the one, not this one. I'm writing for this one, which has the OH on the terminal carbon. Okay, so this is CH2, 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 and OH. This would be the formula. This would be the structural formula. But if this OH was at this place, and here you had an H molecule, so the structural formula is going to change. It's going to become CH3, CH, OH, CH2, and a CH3. Now you see, it's the same molecule, like the molecular formula remains the same, but the structure now differs, right? So the molecular formula remains the same, the structural formula changes, and if you notice, that's the definition of isomerism, right? The structural formula remains, the molecular formula remains the same, the structural formula changes, right? So this basically what happens when you move this OH group. When you move this OH group, the other molecule that are going to form is basically an isomer of that molecule, and that is how it works. And again, the rule is simple. If you attach it at the terminal carbon, like if you have, let's say, if I talk about here, now here, if I talk about putting this OH molecule at this carbon, it's going to make no difference, right? Because both of these carbons are terminal carbons, right? As I said, because the count, if I count from that place, is going to remain the same. If I count from that place, is going to remain the same as well. So that's the simple rule, and that's where we wrap this part. I'm extremely tired right now. Yeah, that's why you're also witnessing the subtle errors in the middle. So yeah, that's where we wrap this part up.